Hey, and welcome to step 4, shipping it off to the testnet. The big thing that we need to change in this step is that we're going to be talking through a bundler to send these user operations onto a live testnet. So a bundler is a party that we have not used in the previous steps. We've taken a bit of a shortcut where we just send our transactions directly to the entry point. We sign them ourselves. But really, if we think about ERC 4337 conceptually from a high level, we know that there's another party involved here, which is a bundler. And a bundler is going to take a bunch of user operations. It's going to maintain its own user operations mempool, and it's going to take those user operations, simulate them, make sure that it's going to get paid back for the gas, and then it's going to put all of those user operations into a transaction and then sign them on chain. So this is sign them and then send them on chain. So this is a really important thing that we need to take use of here, this bundler. So we're going to make use of it in this particular step. The first thing that I did off camera that you'll notice when we come back over to our repository is that I've already gone ahead and got my API key from Alchemy for Arbitrum Sepolia here. So you'll see that I have a .env file where I can access this RPC URL. You're going to want to do this for yourself if you're following along in the guide. And then the other thing is I set up an account with some ether for gas from the faucet here. So you might want to do that as well. So you have some Arbitrum Sepolia ether for gas. Great. So that's all I did. That's all I changed. The one thing that we're definitely going to need to be doing in this step, and I'll be coming back to it in a moment, is using all of these different bundler API endpoints to actually send user operations through and to replace some of the code that we've had in the previous steps, which is kind of janky around gas estimations, right? So we'll want to replace all that stuff. And there's one other thing that we'll need to do that's going to make our user operation compliant with bundler APIs. So we'll take a look at what that is as well. All right, so let's go ahead and jump in here. So you'll notice that I have this .env file. What I did is I put required.env config at the top here. This is just going to go look for that .env file and pull in these process variables here, the RPC URL and my private key. That way I can have those variables available for when we want to deploy stuff to Arbitrum and actually start executing some user operations there. So there is something that I want to do before we get to that point, but in the meantime, what I'm going to do is just for the sake of completeness here, install .env. So that's going to change my package.json. You'll have to do that as well if you want to use this node module for going and loading our .env variables. So now we're ready to be able to interact with the Arbitrum network. But for the moment, I want to change one thing about our account and our account factory in order to make it compliant with bundlers. So one thing that we're going to have to do is in our execute step, right? We have this, let me close out of this here. We have this entry point.handleOps method, which is taking our user operations. We're interacting directly with the entry point. The one thing that we're going to have to change here is we're going to have to use one of those bundler APIs to send a user operation to the bundler, and then the bundler will eventually take that user operation, maybe put it into a bundle with several other user operations, sign them in a transaction, put it on chain. So when we interact with the bundler, one thing that I mentioned a little bit earlier is that the bundler needs to simulate these user operations to make sure that it's going to be paid back the gas for what it is actually signing into the transaction. Because mind you, the bundler is acting as an externally owned account, so it is paying the gas up front, right? But it needs to make sure that it's going to get that gas paid back. So there's a set of rules that user operations have to adhere to in order to make sure that a bundler can successfully simulate and make sure that it's going to be paid back for its gas. So one of those rules that you have to adhere to is this thing called forbidden opcodes. So there's a bunch of opcodes that you cannot use during verification. And the reason is these different opcodes potentially make it so that you could have a simulation of a user operation that would execute differently. Right? When you are able to access different like state variables and things that can change between when the user operation was simulated and when the user operation is actually executed, you could possibly make it so the bundler does not get paid back. Right? And the bundler wants to make sure that it's paid back. So this ERC 4337 standard has put in here a bunch of opcodes that you cannot use during verification. And we actually did use one of these in the previous steps to keep things really simple, which is create. You'll notice here that what you can do is you can use create to when init code is not 0. So we're doing create 1, the original create opcode, when the init code is not 0, but create 2 is the only thing that's allowed. And if you think about this, this makes sense, right? I mentioned this idea that these are opcodes that can potentially change between simulation and execution. And for create, we know that we have that nonce that's in the factory, and every time the factory deploys a new contract, that nonce is going to increase, right? So potentially, when the bundler goes to simulate this, simulating creating an account, potentially that nonce is going to be different between the simulation and when it actually goes to execute, if maybe you interact with it through a different user operation, or maybe even interacting with the account factory directly. Right? So create 2 is a little bit different in that it is going to take in some variables that are a little bit more deterministic so that we can actually simulate what is going to happen and know that it's going to happen the same way during execution. So we'll see what that looks like, because that's the first thing that we need to do in this step is change create over to create 2. Let's go ahead and do that. So I'm going to come into my account, and this is where we're doing our create 1. So when you deploy a contract like this is the typical create opcode, right? So what we need to do is we need to actually change this over to create 2. Create 2 was something that was actually introduced not in the original Ethereum, but over time through a standard. So create 2 is actually a new way to deploy smart contracts that involves a different set of parameters for calculating the address for where that account is going to, or where that smart contract is actually going to land. Luckily for us, OpenZeppelin has some utilities for create 2 as well, which I'm going to make use of here. So inside of utils, I believe we could just look it up there. There's create2.sol. So this is going to be a library of functions that we can pull in to actually do this create 2 contract deployment. So that's what I'm going to use here. It looks like it couldn't find it, but hopefully I did do the import correctly. We'll go take a look at it inside of node modules. Sometimes VS Code has trouble pulling that up for whatever reason. So if we go to OpenZeppelin contracts, utils, and yeah, it looks like create 2 is right here. So this is going to use create 2. Now create 2, the things that it uses to determine what the address are going to be is this bytecode and salt. So if you supply the same bytecode and the same salt, it's going to end up deploying a smart contract to the same address. And this is why it can be the same for simulation and execution of a user operation, because that bytecode and salt is going to be supplied through the call data of the user operation, right? So we know that when the user operation is being simulated, the same execution is going to occur for a bundler. It's a pretty nuanced take, right? It's like a little bit hard to see that without like diving into the code maybe, or maybe you understand that directly. That'd be awesome if you do. But nonetheless, this is what we need to do. We need to pass this through with create 2. So we're going to pass through bytecode and salt. What we need to do is we need to use this deploy method. This amount is something that we're not going to use. This would be if we wanted to send some ether or the native gas money here into the deployed contract. We're not going to use that. We're going to pass through 0. This salt is something that you could change. Like we're just going to, for this step, I'm just going to make it so when somebody wants to deploy a smart account through our Account Factory, they're always going to deploy it to the same address. But if you wanted to make it so that users can deploy multiple smart contracts, multiple smart accounts, you could change the salt every time for that sender, for that person who is actually trying to deploy the smart account, right? And then the bytecode is going to be the actual creation code plus the constructor arguments for this account. So let's see this a little bit more in code, where it'll make a little bit more sense. So I'm going to pull over this deploy function, and I'm going to use create2 dot deploy. And then we know, so the arguments are going to be that amount, it's going to be the salt, and it's going to be the bytecode. So that's what we're going to need to do here instead of what we did before. And the amount, like I said, is going to be the amount of ether that we want to send through to the constructor. I don't want to send anything over. Our constructor is not payable. It's not something that takes ether, so nothing needs to be sent through there. So for the salt, what I'm going to do to keep things really simple for us is I'm just going to make it so that this owner, when they want to deploy an account, they're just going to always be referring to the same account every time, right? So I'm not going to have a different salt here. I'm just going to go ahead and use the owner as a salt here. That way, somebody else who deploys an account will have a different address for their smart account, but every time the same owner tries to interact with a smart account, they're going to get that same address. This is also going to make things a little bit simpler over inside of our execute, where we can get rid of some of this code where we send over this init code. We can actually go and look up whether or not that smart contract has some code, and then be able to more smartly execute the user operation rather than having to comment this out every time like I've been doing in the previous steps. So let's go ahead, and for the salt, what I'm going to, the salt is going to be a bytes 32, I believe, right? Yeah, bytes 32 for the salt. So what we're going to need to do for the salt is I am just going to cast the address owner into a bytes 32. Now this is a little bit harder than you would think it is. There may be an easier way to do this in Solidity, but what I'm going to do is I'm going to cast it to an address is 20 bytes, so it's 160 bits. So I'm going to cast it over to a uint 160, and then cast that to a uint 256, and then cast that to a bytes 32. We can't do it more directly than that. We do have to go into an unsigned integer and then into a bytes 32. There's probably an easier way to do this in assembly. I don't know if there's an easier way to do this in Solidity. If there is, let me know in the comments below. That would be great. But this is what I'm going to do here to be able to cast that owner. So now the owner is going to be the salt. So this is going to help us calculate the address for that smart contract that is going to be deployed, right? And the owner every time is going to be referring to the same smart contract because it's going to have the same salt. And then the bytecode is going to be the same. The bytecode is going to be a bytes argument. So we're going to pass in bytes. The bytecode here is going to be ABI encode packed. We're actually going to be passing in here for the first thing is going to be the creation code. Now, I always forget how to do this, but lucky for us, again, OpenZeppelin is doing awesome stuff here. Not only did they create the utilities for us, the library, but they also in the comments gave us a good understanding of how we could use this library. They say, use type here, the contract name, and then .creation code to actually get the creation code. So that's awesome. So what I can do is I can get the creation code of the account here. And then the other thing that I'm going to need to do here is pack it with the constructor arguments, right? I mentioned that earlier. The bytecode for actually deploying a smart contract is going to be the creation code of the contract itself, which we can get from this here, and then the constructor arguments. So I need to pass in here the owner because the constructor argument owner is going to be passed through to our account right here, right? There's one more thing I need to do here, which again, this gets a little bit low level. For the constructor arguments here for our owner, this is actually going to have to be padded, this argument. So I'm going to do ABI encode. If I didn't do that ABI encode, this address wouldn't actually be padded, and that just doesn't adhere to what we need to do for creation code. So that's a small thing, but really important that we do that there. So I'm going to go ahead and do that, and then here's the bytecode. Okay, sweet. So that was a lot to get Create 2 to work. You could see why I kind of avoided it in the previous steps until I needed to do it now. I like to keep things simple until that very moment where we need something. But at the end of the day, this is rather similar to what we were doing before, where we were saying new account and then just passing over the owner. The difference is we're using Create 2 now instead of the original Create opcode, and we're using variables that are being passed through to us, the salt and the bytecode, so that the bundler knows that when it goes to simulate this, it's going to happen the exact same way in execution. It's not referring to some sort of state like the nonce would in the account factory. That's something that can change between simulation and execution, right? That's a big thing that we did here that we changed. Create2.deploy should return me an address. Yeah, there it is right there, right? Which we do need to return here for this create account factory. And there we go, we have it. So one more thing that I do want to do with this account factory create account function is that I do want to make it work with this other method inside of the entry point. So this way we can actually just go look up that address from the entry point every time that we want to use it. So this is something that I know exists inside of our account abstraction core entry point, there's a method called like get sender address. Yeah, okay. Get sender address that gets the counterfactual sender address, right? That's a big word, counterfactual. Basically means that we can calculate this address ahead of time. We know what the address is going to be, so we can calculate it ahead of time. Technically, with a counterfactual address, if you know what the address is going to be in the future, you can already start sending NFTs and tokens to an address before it's even deployed, right? This is why the term counterfactual is being used here. You could start to use the address before it's deployed because you know what the salt and the bytecode are going to be. Therefore, you know what that address is going to eventually be. I want to make this account factory, this method, create account, able to be used with this get sender address. So we are going to need to make it return an address even when it's initialized, because this method is going to use that create sender, the sender creator, to get that address result. So in order to make it work with this get sender address method, what I'm going to do is I'm going to have this return the address of this this account that we're deploying, even if the account is already deployed. So that's going to change a few things here. So what I'm going to need to do is I'm also going to need to compute this address in the instance that it's already deployed. So computing it, we can do it by going back to our create2. Dang. Okay, I lost my create2, so I'm just going to need to pull it back up again. Let's go into Open Zeppelin, utils, create2, there it is. And then there's this compute address method, which takes a salt and a bytecode hash, right? Not the bytecode hash, which is just going to be the catch-check hash of that bytecode. So let's go ahead and take this compute address here, and we're going to get the address, the counterfactual address, which is the address of the thing that we're going to deploy if it's not already deployed, right? So our address is going to be compute address, create2.compute address, and it's going to take the salt and then the catch-check hash of the bytecode. Sweet. So now what we need to do is we need to say if the address.code.length is greater than 0, then we are going to go ahead and just return the address here. That way, if there's already code at that location, we could just say, here's the address, and that sender creator method, this get sender address, inside of my account abstraction entry point here is going to be able to, I need to double click on these so they actually stay up here. This is going to always return that sender address for us, so we can make use of that rather than having to calculate it ourselves. Great. Okay, so now what we need to do is test this. So that's why I haven't started working with Arbitrum yet, is I need us to actually go ahead and test this on our local network. That's going to be the easiest way to do it. So I've kept the default network to be localhost. Again, what I'm going to do is I'm going to create a hard hat node and run this locally, so that way we can interact with this local hard hat node and be able to more easily just deploy stuff and test it out before we try it on a testnet and use some of that testnet ether that we got from the faucet. So let's go ahead and deploy this and make sure that everything is working properly. So what we're going to need to do inside of our execute is a couple things. So now this get create address and this factory non stuff that was kind of hokey before can go away. First off, we're not going to be calculating this ahead of time. We're going to be using that method on the entry point, the get sender address. So we don't need this here anymore. Also, I want to make it so that the init code is always calculated, because we're going to use that init code within this get sender address to actually get that address, get that counterfactual address every time. So I'm going to be sending that through, and then we're going to use that method. We're going to say, we already have the entry point here, thankfully. We could say entry point.getSenderAddress and pass in the init code, and this should get us the sender address every time for this factory address plus this create account. This is going to be the salt here, this address 0, so we should get the same counterfactual address every time for this particular address 0 in our implementation, right? So I'll say get sender address. Now there's a bit of a problem here in the way that get sender address works, and this is again due to some of the things that we need to be concerned about in ERC 4337, is that we have this method that is always going to be, it is always going to revert revert. So that's a little bit weird. You see there's no return value here. So in order to actually get this sender, we're going to have to parse it out of the thrown error here. So that's a little strange. So we're going to have to try that out here to see if we can get that data out. So I'm going to say try this and then catch it. And I'm going to put in a wait in here because that's going to be a promise. And then we're going to log out the x.data to see what's inside of the exception and see what we're getting back so that we could parse out that address that is being calculated for this particular init code. And then I don't need any of this for now, so I'm just going to comment it out. And we're also going to move this paymaster stuff out of here. So that way we can just keep running execute without having to comment and uncomment out stuff like we did in the previous steps. So we can kind of clean all this stuff up here. Cool. So this should get us to the point where we are throwing that error and hopefully we can see what that sender address is. So let me go ahead and run npx hardhat run scripts/execute. And we're still running this against our local node, which I forgot to deploy contracts to. So let's do that first. Let me go ahead and do deploy. And bytecode. We need to come back over here and give it, because this is a variable that needs to have a memory location, a data location. We need to put one here. So I'm going to put memory for our bytecode. And yeah, now we should be in good shape. So let's go ahead and deploy. All right, sweet. So hopefully these addresses are similar to the ones that we had, or the same as the ones that we had in execute here. We don't have to change them. Let's see. I have something in the way, but yeah, it looks to be the same ones here. Great. So I don't need to change them here. And we can go ahead and execute and see if we get that sender address. Okay, so we could see, sorry, I got the screen recording thing in the way here. I want to try to move it, but okay, there it goes. Sorry. So we can see here we have in the data, so this is going to be the signature for the error that is being thrown. So this sender address result, this is the signature for it right here, which is similar to call data methods. You take the catch-check hash of the signature of the exception because it's a custom error. And then from here, we have the padded address. So if we want to get this address, this is going to be our sender address. If we want to get it, we could parse it out of the data field here. So it's actually going to be data, right? So it's going to be x.data.data. And then we want to slice off the last 20 bytes, which is in hexadecimal 40 characters. So we're going to say -40 there. So our sender address is actually going to be this thing that we're going to parse out of an exception here. Yeah, this is pretty wild, huh? So we're going to go ahead and do that, and then we can log out that sender. So hopefully if this slices off properly, we'll grab these last 40 characters off of our hexadecimal data there, and then that'll be our sender address. Maybe we should add a 0x to this, right? So it's a hex encoded string, and yeah, so we shouldn't run into any issues below. And there we go. So that's our sender address. So this should be the sender address every time for that init code for this particular address 0, because we were passing that init code in creating a counterfactual create to address. So we should get the same one every time. Something we might want to do here now that we're up to this point, is also make our script a little bit smarter, where it could say something like, let's first log it out to make sure that it's working, but we could say await ethers.provider.getCode. Is it get code? I think so. Yeah, looks like it's coming up. We'll say get code at this sender address, and we'll be able to see whether or not this this sender has already been deployed. The account has already been deployed. So let me just log that out. It shouldn't be deployed, right? Because we haven't run the opcode yet, but for future opcodes, it'll already be deployed. So this is going to be, what we can do here is we could say the code is going to be that, and we could say if code or we could say if code is not equal to 0x, then what do we want to do? We want to make it so that the init code isn't passed through, because the init code, we only want to pass it through when we're trying to initialize the sender. If it's not initialized, then we want to send through the init code because we actually want to create the account. But if it is initialized and the code is not equal to 0x, then we actually want to make the init code 0x here. So we're going to have to change this from a const to a let. And so the init code can actually be changed here if we've already deployed the smart account. This is going to make it so I don't have to comment out and comment back in like I've been doing in the previous steps, this code here, which is super nice. So we can actually just keep running execute regardless of whether we're deploying that smart account for the first time or whether we're just executing against it each time. So that's super sweet. Okay, so we'll continue to log out the sender here. I'm going to take over the PM address here. This deposit, I want to put in its own script because this is also something that we only need to do once. So let's just go ahead and put it in its own script. So we'll have a PM address, and then this is all we're going to do is we're going to have our entry point. We also want to get our entry point address. So I want to leave that up there because we're going to deposit to the entry point for the PM address. And we're just going to leave this here. And then we'll say something along the lines of like deposit was successful, right? Because otherwise we'll throw an exception if that deposit was not successful. And sweet. So great. So we're depositing to the entry point. When we do this on testnet, we're going to want to do a smaller amount. I don't have a ton in my account there, so I'm just going to do 0.2, and that should be plenty for user operations. And now we can get rid of that code out of our execute. So now our execute function is starting to shape up as something that we can actually run again and again and again without having to comment out and comment back in everything. We can actually say, regardless of whether we're deploying that smart contract for the first time, it'll run, and then we should only deposit once on the paymaster. Great. So then we could comment all this back in, and maybe we could just test to make sure that this is working locally before we go ahead and move over to the testnet. So let's go ahead and we've already deployed everything, and I haven't changed my account since then, and I already have some funds in the paymaster. So let's just go ahead and execute there and see if it's working. So it looks like, okay, maybe I didn't deposit in the paymaster. Oh, that's right. It was commented out. So let's go ahead and run that deposit to deposit against our paymaster. And then we can go ahead and execute. And there we go. So we'll get our sender address and make sure that that's working properly. We should have upgraded that account a couple times. And the sender address should be the same every time, right? There it is that time, and there it is that time. So we're getting that same address every time that we run it. And then we say test.js, and there we go. Our account is 2. If we ran it again, it would be account is 3, account is 4, and we could test it. And if we had a different address, right, we could even do, if this was address 1, then we'd have to sign it with the signer 1. So yeah, maybe we could do that. We could do address 1, signer1.getAddress, pass this through, create an account for them. That's going to be a different account. And then when we want to actually get the signature, we have to do signer1.signMessage, right? Because it's going to be validated by the account. And then we could do the same thing here where it's going to deploy the smart account the first time. And then it's going to, and then we could test it. It's going to be a different address, right? This is for somebody else. This is for the address 1. So this one's going to actually have an account of 1, and then we could keep running against them. And we could see this execute function has gotten a lot smoother, right? Because now I don't have to worry about, is the smart account already deployed? It figures that out for me. It goes ahead and does all that stuff. So we could even switch back to the original signer as long as we switch the code back over here where we sign with sign 0 and we get the address with address 0. So that way it goes and gets that counterfactual address for that first signer. And we can execute that one, and the count should go up for the first one. Great. Okay, so that's working really, really well on our local network. That was the thing that we needed to change in order to make our user operations compatible with the bundler. So now we are actually good to move forward with actually deploying this to the testnet. Now, the other things that we're going to need to do in order to get this to be working well on the testnet is that we actually want to make these real values, right? These are just fake values that I plugged in. So we're going to want to actually use APIs to get these values. So I'm going to move these out. These are no longer going to be what we want to use them. So I'm going to comment them out for now, just so we remember all the different variables that we need to replace. And what we'll do here is these first 3 all come from the same API, which we can actually find over here on the bundler API endpoints. They are all going to come from this estimate user operation gas. So we can actually pass through the user operation to this estimate user operation gas. And if we take a look at the response, is what we want. We want these three gas values: pre-verification gas, verification gas limit, and the call gas limit. So fortunately, we have that simulation that can go out and actually go and grab those things, so we can actually put them in and have real values inside of our user operation, rather than something that I just made up. And you saw in the previous step, I was wrong, right? I needed to add some more buffer room in there. So we want to make sure that we actually use something here that's going to work every time, right? That's a point, is make this execute script something that we just keep running regardless of if we switch some of this stuff every time. So what we're going to need to do is we're going to need to use ethers.provider.send. This is going to take a method. So we're going to key into this provider, which is going to be the RPC that I encoded from my .env that's going into the hard hat config. We're going to be talking to Arbitrum Sepolia every time in our scripts now. So I'm going to change my default network over to Arb, so that way I don't have to pass it in on a flag every time I run the scripts. So now we're actually going to be talking to that RPC URL with a private key. This private key is eventually just going to be used for signing the user operation, and then the bundler is actually going to sign the transaction, right? So this is really just the one that gives us the ability to execute something against that smart account. Great. So this ETH estimate user operation gas is going to be talking to my Alchemy API endpoint, which is going to be talking to Arbitrum Sepolia, so we can know that we're going to get the specific gas values for talking to that testnet with this particular user operation. So if I want to look up what that response is going to be, let's go ahead and do this, and we're going to say estimate user operation gas. Now the arguments that are passed in here, we do need to look at here. It's going to be the user operation and then the entry point. Now the entry point is something, so we haven't deployed on the testnet, right? We need to go through and deploy all the smart contracts that we've been deploying on the testnet as well. So what I'm going to need to do here is I'm going to need to go over to supported entry points, and then we are going to need to grab this supported entry point right here and actually put that into our entry point address right here. So this is what we're going to need to do. We're going to need to take that entry point address and plug it in there, and then we are going to use that as one of our arguments here. So we'll take the entry point address, and then we're also going to pass in the user operation. So these two things are going to go to this estimate user operation gas method, and then that should get us a response here for the user operation. One more thing that we have to do, and you can see it's in a big bubble for this method over here, is that we have this thing that's saying that you need to pass in like a dummy signature into this method. So you will need to replace that signature here with this dummy signature. That's one thing to watch out for. The other thing that I already know is going to be an issue is this get nonce method is actually going to return a big number or a big integer, which is a standard JavaScript variable now, or variable type. So what we need to do is we need to transform this into a hex encoded string. So I'm just going to go ahead and do that. So I'm going to say toString 16. Otherwise, that's going to be a problem for this particular API. So I just want to make sure that that's all encoded properly. And then we'll send to estimate user operation gas, and we should get this response. Let's go ahead and log it to make sure everything's working properly and see that we're getting those gas variables back. So I'm going to go ahead and execute. Okay, so it's saying that it doesn't know. It's saying it's having a problem with this slice variable here. So let's just log out the exception. Something might have changed about that data there. This is kind of hokey code here, right? So taking something out of the execution. So one thing that might be an issue is that I haven't deployed the factory yet, right? And we are encoding against the factory. And in order to go get that, so all right, I do need to deploy the factory first before we can actually test all this stuff out. So let me just go back and do this deployment stuff. We do not need to deploy the entry point, right? Because we are going to be using the standard entry point for Arbitrum Sepolia. That's the supported entry point that I just grabbed. But we are going to deploy the account factory and also the paymaster. So let's go ahead and deploy those now. We'll do scripts.deploy.js. And we have our Account Factory deployed and we have our Paymaster deployed. The other thing that we're going to want to do is we're going to want to go ahead and deposit some funds to our Paymaster at the correct entry point here. So let's go ahead and do that. Let's deposit. So we're going to have to do scripts/deposit.js. And then there's the deposit was successful. Cool. So we put the 0.2 Ether over there. Awesome. And then now we can actually take those addresses and put them into execute here, right? So we have the Account Factory is going to be this one. This is the supported entry point that's already deployed. That way we can all use the same entry point. We don't have to deploy it all in every place in the testnet. So this is one of the entry points that we can use here. And then we have this Paymaster address that already has some funds deposited on the entry point for us. Great. Okay, so now we should be able to test out this execute function. So let's go ahead and do that. I'm going to do execute here. And we can see that, okay, so it's still having trouble with the reading slice here of undefined, but the error that we're getting is just that the execution was reverted. So I wonder if there's something else going on. We did pass in the correct Account Factory and we did pass in the correct PM address here. And we're passing to the entry point the get sender address. What else is going on here? So there's something else going wrong here, because I do expect that this x.data. Oh, look at that. Okay. So yes, yeah, this exception stuff is really tough to do. This is why you should be using the account kit, which is we've rolled up all of this logic into a tool that you can use. That's going to be much easier to do than doing all this stuff yourself. Pulling data out of an exception is really janky code. So you can see that in the x.data now is actually the address here. This is what we want. We don't want x.data.data. So clearly this is working differently when we do this against the testnet versus the local hard hat network. I can't tell you why that's the case, why this exception is coming back differently. You know, when running local blockchain nodes versus running a live testnet node, you're just going to have differences in behavior. So there you go. So that the sender address actually came in here in x.data instead of data.data. So there we go. We'll get that sender address, and then hopefully now we can get that estimate user operation gas coming through. And user operation was not an argument. It looks like I got my parameters backwards. I thought I could do it either way. Cool. So there we go. We got our three values here. We got the pre-verification gas. We got the verification gas limit. And then we got the call gas limit. Sweet. And then we can plug these into our user operation. So we can go ahead and replace those values. Pre-verification gas, pre-verification gas. Verification gas limit is verification gas limit. And then UserOp.call gas limit is call gas limit. All right, awesome. Okay, cool. So now we have that. So we got rid of these three. The other things that we need to do are this max fee per gas and max priority fee per gas. Again, like I said, Account Kit is going to wrap all this stuff up for you. But I do know that for max fee per gas, we got to get this from just like a standard API. And for the max priority fee per gas, the bundler, the Alchemy bundler is going to have a specific value that you need to plug in here for the max priority fee per gas. So for the max fee per gas, we can go ahead and get that from ethers. So we could say, let's just get response here is going to be equal to, I want to comment all this stuff out for now so we don't do any of that. Our response is going to be equal to await ethers.provider.get fee data. And let's just log this out because I forget what the response is going to look like, but we should get that max fee per gas. Let's go ahead and execute that. Okay, so there's the max fee per gas. We're going to make use of that here. The max fee per gas is going to be our UserOp.max fee per gas. Again, I know that we need to actually hex encode this, so I'm going to say max fee per gas, toString 16. So that way we can actually get that as a hex encoded string instead of a big int. As you can see, it's being passed down below. And then for the max priority fee per gas, we actually need to use a bundler API for this one. So we're going to call out to that again. Similar to what we did here, we're going to say await ethers.provider.send, but this is going to be a method called Runler max priority fee per gas. So you can use this against whatever network you happen to be on, and you can get the max priority fee per gas that we're suggesting that you use from the Alchemy bundler called the Runler. So this doesn't require any arguments here. This is just going to give us the value for the max priority fee per gas at that time. So what we expect to get back here is that max priority fee per gas, and then we can go ahead and plug this onto the user operation as well. Also, like if you notice, I'm not programming very defensively here, right? Like if any of these fail, like what happens then? This is the sort of stuff that could be wrapped up in a library. It's pretty difficult to do a lot of this stuff yourself, but you know, just for learning purposes, that's where we are. And so we can get rid of these here as well. And then we have the whole signature thing set up perfectly fine. The only other thing that we need to do at this point is just go ahead and send this, instead of the entry point, we need to send this to the bundler itself. So that's where we're going to be using await ethers.provider.send, and then there's a method called send user operation. Here we go. So we'll say eth send user operation. The parameters here are going to be the user operation and then the entry point. So we'll send through the user op and then the entry point address. What did I do up here for that? EP address. There we go. So we'll send that through, and this should return us a user op hash, which is going to be good enough for me to consider this successful here. Let's just call this op hash, and then we'll just log that out. Now, behind the scenes, a user op hash just means that this user operation has been accepted. It's in the mempool. Doesn't mean that the transaction has actually worked just yet. But let's just see if we can get this to log out and then see if we could get that test to work where we're actually incrementing a count. So let's go ahead and run execute. Signature value was not a string. Okay, so what is the signature value? Let's go ahead and log user op. Oh, it's a promise. All right, so I guess that was handled when we were using it like this, the handle ops. Ethers must have resolved that promise. But here, when we're sending it through to this API, we need to make sure to resolve that ourselves because we're just sending it straight through Ethers provider. So just await that, and then we're good. And factory uses banned opcode self-balance. That's interesting. Where do we use self-balance here? Okay, so where's this operation code coming from, this self-balance? This took me a moment to figure out. This self-balance obviously is one of the forbidden opcodes that we talked about, and you can see it in here as well. When you're looking up the balance of a smart contract, of course, that's something that can change from simulation to the execution of the user operation. So it's something that we wouldn't want to have in here either. Now, naturally, in my account, there's nowhere in here that I am doing a self-balance, so I figured that it must have been one of the libraries that we're using, and it turns out that create2.deploy actually does use a balance check. So if we go in here, let's see if it'll bring it up. You can see that it's doing this thing where I said I'm not using this amount, but it's still doing this check on the smart contract to see whether or not there's a balance here. So this is actually not okay to be using within our user operations within 4337 here, because like I said, the bundler needs to simulate it and then run it. So we can't use this opcode here. So that's a really interesting thing to realize. I thought that I had run through this before with this particular deploy method, but maybe there was something different about that test that I had done this once before with. So what we actually will have to do here is just modify this function ever so slightly. I'm not going to be using this amount anyway, so maybe we can just bring this one over into our account And what we'll do is, well, for this case, I don't even really need to take in an amount, right? Like I said, I'm not going to use it, so I'm not going to take it in, and I'm going to get rid of this line of code here. And then for the amount in my create to, I'm just going to pass in 0. So now we have our own deploy. I still like that computer address method, and still going to come up with the same address as our sender, so I'm going to keep that in there from the create to library. But we will change this deploy method so that we can just say deploy, pass in the salt and the bytecode, and then we won't be doing that self-balance check. So we should not run into this issue again if we were to redeploy. This time for deployment, I'm just going to deploy the account factory since we already deployed our paymaster and we've deposited funds on the entry point for the paymaster. I'm not going to do that again. I'm just going to go ahead and deploy this account factory, and now we have a new one. And what I'll do is I'll take that one and put it in here for the execute. There's no reason why that paymaster that we deployed before shouldn't be able to pay for this new account here. So we should just be able to run everything else accordingly. And hopefully we have no more buried forbidden opcodes inside there and can just run this from this point on. So if I do execute.js here now, hopefully we'll see a user operation going through. So that looks promising. Here is our sender. Hopefully the sender address is the same every time. So if I execute again, we'll get that same sender address. Awesome. So I've now sent this through twice. It looks like 2 user operation hashes. Now, mind you, these user operation hashes right here do not necessarily mean that the transaction went through. It means the user op was received and there were no issues that arose immediately. So we can go check to see if those user operations actually went through, and I'll show you how to do that through the API. But for now, let's just take this sender here and see whether or not our count was increased, right? So let's just go ahead and run test and see if that was increased on Arbitrum Sepolia, and looks like it's 2, and we could keep executing and we should be able to get 3 and so on and so forth, right? Super cool. So awesome. So that looks like it's working really well. And that is everything that we needed to do here. So if we wanted to maybe just check if we go to like Arbitrum Sepolia Etherscan and we want to just put it in here and then just take a look. I don't know why I call it Etherscan even when it's Arbiscan. It's just like the name, right? So there is the sender address here, the smart account, and we could see that there's some contract code here that's not verified, and then we could see that there's some internal transactions happening against this. It doesn't look like I see some of the transactions from the user ops that I wanted to find. There's only really contract creation here. Sometimes this doesn't get indexed super quickly. So maybe what we should do is we should just also get the transaction hash here so we can find it on Arbiscan. So what I'm going to do is this user op hash, we can use this to go look up the user operation using this other bundler endpoint, which is called get user operation by hash. So we're going to go ahead and use this one here, and we'll take our hash and we'll plug it into this method here, get user operation by hash. And then this is going to take as an argument just the user operation hash, right? As you might expect. So we'll pass that in as our argument. And then what we should get back, the only thing that we really care about in here, I mean, you can see you get like basically the whole user op back plus more information, like the block number, block hash, and transaction hash. I only care about the transaction hash here because I want to go look it up on Arbitrum Scan just to be able to see more information about it. So I'm going to log out the transaction hash. Now, one thing we are going to have to do here that's a bit awkward is just sort of guess at how long it's going to take for this transaction to actually get included in the blockchain. So, you know, things like the account kit are going to handle this for you, where they're going to keep checking to see whether the transaction has been included. But for our particular case, the only thing we really can do is set a timeout here, maybe do a loop of like checking to see whether or not that transaction has been included. So I'm going to do a pretty safe buffer here and just say, let's wait 5 seconds. And then those 5 seconds should be enough for us to go get that transaction at that point. It should be included by that point, and then we should be good. So let's go ahead and see that transaction hash as it comes through, and then we'll be able to go look it up. So I'll go ahead and execute that. Now it's going to run, and we're going to have to wait 5 seconds. So I'm going to stall, or I can count to 5. But I think I stalled long enough. There we go. All right, here's our transaction hash, right? So we'll pull this on over. And if we go to Arbiscan and instead of address, we do transaction, pass that in. Here is our transaction. You could see this is coming from no longer, you'll have to trust me that this isn't my address, this is the bundler here. So the bundler has been doing a lot of transactions. You can see they have a significant balance here. So the bundler is actually signing the transactions now, which means, this is the cool thing, and we could see this in a second, we no longer have to keep gas in our account in order to be able to interact with this smart account, right? We can actually have an account that has no gas inside of it, and because it's being sponsored by the Paymaster, we don't have to worry about that, right? The bundler is the one who's signing the transaction, so they are paying the gas up front, but they're getting paid back by the entry point through those gas calculations that the entry point is doing. So yeah, that's where this is coming from. You can see the bundler is calling this handle ops method. It's been doing this for a whole bunch of these methods that people are testing this bundler on the Arbitrum Sepolia network. Sweet. So that is everything that we need to do. Maybe just to have a little bit of fun with it, what we can do is we can replace the private key with just one that I just generate here, right? Because now we could use any account to deploy a smart account, right? Because we don't, any externally owned account, because all it needs to do, this externally owned account, is act as a signer for the user operation. So something that would be a little fun here is maybe if I could just require crypto and then do random bytes 32, two-string 16, two-string hex. Oops. And then that's going to give me a private key. Here's a private key. I'll never put any real funds on this. You should not either. Do not use private keys that you see in these videos. Here we're going to go over here to this private key. Instead of using the one that I have in process env, I'm just going to plug in this one, right? This is going to give us access to some account on chain that should have no funds in it. It's a randomly generated private key. And what I'm just going to use it for is just signing the user operation, right? Because now we no longer have to keep gas in our account. We could just sign a user operation with this private key. And then that user operation is going to be sent on chain by the bundler. The bundler is going to pay for the gas up front and then be paid back, right? Awesome. So what we do need to do though is, well, actually, do we need to do anything? So we don't need to redeploy the account factory, right? Because the account factory is just there waiting for us to send in some init code from an account. So I don't think we need to redeploy anything. The only thing we need to do, sender 0 or signer 0 is now going to be this new private key that we just came up with, which should create a new address. I don't think we have to do anything. I think we could just run execute and we should be able to have a new smart account that we're executing against. I'm crossing my fingers here. 5 seconds. 4, 3, 2, 1. Sweet. There's a new transaction. This is a sender who has a new smart account from a private key that we just generated, right? And then we can go out here to TX, pass that in, boom. Looks like we have a user operation that's executed on chain by the same bundler. There's our bundler again, right? Being sponsored by the Paymaster through a new private key. Right now, this private key, all it does is it secures that smart account, right? It does not have to, all this private key is being used for is securing the smart account. It does not have to pay for gas. We don't have to care about the address that it owns on chain. It's not being used like an externally owned account. So its address is really, for all intents and purposes, not important. We don't really care about what its address is on chain because we're kind of circumventing that with account abstraction, right? This address is, or this private key, the more important function that it serves now is the authentication of the smart contract itself in that abstracted signature that we have there at the end. So super cool. We did everything that we intended to do with this step. Hopefully you learned a whole lot about smart accounts, about paymasters and the entry point through this series. And the next thing that I challenge you to do is move on to the account kit. Check out the account kit through the docs below. Everything that you learned in these previous videos is going to make you a power user of the account kit. So you'll really understand everything it's doing behind the scenes so you can build awesome user experiences for your Web3 users.